In section 5.1, we saw that terminal points on the unit circle had certain x, y values. In this section, we'll see that certain right triangles determine these values. Before we go any further, let me go ahead and note that the default angle measure for trig functions is radians. Let's look at special right triangles now. The first one we'll be looking at is the 45-45-90 triangle. To first construct this triangle, let's take a square with side length 1. Then we'll bisect an angle of the square. Since a square has each angle equal to 90 degrees, by bisecting it, we've created two angles with 45 degrees. Now we know all the angles of the triangle that we just constructed, the 45-45-90. We know two sides, which means we can find the third side using the Pythagorean theorem, which is going to be then the square root of 2. Now we can go ahead and divide each side by the square root of 2 to construct a similar triangle. And now this new triangle determines a point on the unit circle. So this would be our point on the unit circle if this was the origin. And the values of this point would be given by the following: square root of 2 divided by 2 and square root of 2 divided by 2. Now let's go ahead and look at the 30-60-90 triangle and see where the points would lie on the unit circle. To construct a 30-60-90 triangle, take an equilateral triangle and we'll let the length of each side be 1. So here's our equilateral triangle, side 1. Then a common known fact is that the angle is equal to 60 degrees for each angle in an equilateral triangle. We can go ahead and bisect any given angle we want. Again, bisecting an angle creates two angles of 30 degrees. And finally, by drawing a straight line, we've also introduced an angle of 90 degrees. Since we split the base of our equilateral triangle in half, this length here is 1/2. And again, we can find the length of the final side by using the Pythagorean theorem. So we'll have a squared plus b squared is equal to c squared. In this case, c squared is 1, a squared is 1/2, and we're trying to solve for b squared, which means we're going to get b squared is equal to 3 divided by 4, and then b is going to be the square root of 3 divided by 4, which is the square root of 3 divided by 2. Again, we can place this right triangle inside our unit circle. So let's look at this point here, and let's suppose that this angle here is 60 degrees. Well, this angle here would be 30 degrees. And by what we constructed, this side is given by length 1, this bottom side is given by length 1/2, and the right-hand side has length square root of 3 divided by 2, which means this point on the unit circle would be given by the point 1/2 comma square root of 3 divided by 2. Now if we again looked at the unit circle, but this time we formed an angle of 30 degrees, then when we form our right triangle, this angle right here would be 60 degrees, and the opposite side would have length 1/2, the adjacent side would have length square root of 3 divided by 2, and the radius is still 1. So the point that lies on the unit circle would then be the point square root of 3 divided by 2, 1/2. And we see that this is where the x and y values on the unit circle appeared for terminal points, from these special right triangles. Let's go ahead and find all the angles and all the sides of a given right triangle that's not necessarily a special right triangle. Example number 2. Suppose we're given the following right triangle. This side has length B, this side has length C, this side has length 106, this is 90 degrees, this is pi divided by 5, and this side has length x. In this problem, we want to find the side to length C, the side to length B, and also the angle x. One thing that we know about triangles is that the sum of angles of a right triangle is pi. And we know that 90 degrees is the same thing as pi divided by 2. So the sum of the things that we do know is that pi divided by 2 plus pi divided by 5 plus the unknown x needs to be equal to pi itself. We can go ahead and just solve for solve for x, and we'll see that x is going to be equal to 3 pi divided by 10. So now we'll use trig ratios to solve for the length of the sides C and the length of the side B. Let's look at the sign of pi divided by 5. The sign of pi divided by 5 is equal to the opposite divided by the hypotenuse. In this case, we know the opposite has length 106 divided by C. Solving for C, we're going to get that C is equal to 106 divided by sine of pi divided by 5. Since we already found that x is equal to 3 pi divided by 10, we can also see that the cosine of 3 pi divided by 10 is equal to the adjacent side, 106, also divided by c. So this would be an alternate way to find what c could be. We'd either use sine or cosine, but we'll stick to this first one here. So let me go ahead and copy some of this information and bring it to the next page. Okay, so we have an answer for what the hypotenuse has to be. Let's go ahead and find what our side B has to be. Again, let's go ahead and use pi divided by 5 as our angle. And if we use cosine, again, we'll have two unknowns. Instead, let's go ahead and use tan theta. Tan of pi divided by 5 is going to be equal to opposite divided by adjacent, which is going to be 106 divided by b. Solving for b, we get b is going to be equal to 106 divided by tan of pi divided by 5. Then, again, in this case, the length of side b is 106 divided by tan of pi divided by 5. Before we go any further, let's go ahead and use a calculator in Mathematica to approximate what the side length of C is going to be. Here we need to go ahead and calculate what sine of pi divided by 5 is equal to. So to do this, we can type into Mathematica the following: capital S-I-N of capital P-I divided by 5. And what we'll get out is that this is approximately 0.5877. So this is then going to be equal to about 106 divided by 0.5877, which once we plug this into a calculator, we should get that this is about 180.364. And this is going to be a numerical approximation of what C is. Before we go any further, let's go ahead and look at some trig identities. In this first identity, what we're saying is that cosecant theta is equal to the reciprocal of sine theta, secant theta is equal to the reciprocal of cosine theta, cotan theta is equal to the reciprocal of tan theta, and tan theta is equivalent to sine theta divided by cosine theta. All these identities follow from the definition of the trig functions that we've seen before, but let's go ahead and write and show one of these identities. Let's look at tan theta. By definition, tan theta is going to be equal to the opposite side divided by the adjacent side, which is y divided by x. Multiplying the top and the bottom by r, we can rewrite this as y divided by r divided by x divided by r, where r is the radius of our triangle. Then this is equal to sine theta divided by cosine theta. Let's look at one more example in this section, example number 3. Let's evaluate the following trig function without a calculator. To do so, let's go ahead and draw the triangle that's defined by the angle theta. So here's our unit circle. We have a triangle that forms an angle with the origin of pi divided by 6. This is pi divided by 6, which means we're going to have a 30, 60, 90 triangle. Since we know this has a radius of 1, the hypotenuse of this triangle has length 1. Pi divided by 6 has a side of length 1 divided by 2, and it's adjacent to the side of length square root of 3 divided by 2. Then sine of pi divided by 6 is equal to opposite divided by the hypotenuse, so 1/2 divided by 1, which is 1/2 again. Then cosecant of pi divided by 6 is equal to 1 divided by sine of pi divided by 6, which is going to be equal to 1 divided by 1 divided by 2, which is 2. And what we get is that this is going to be equal to 1/2 plus 2, which is 2.5.